Welcome back to the session on finite differences. In the previous session, we discussed some relations connecting the forward difference operator delta and the shift operator E. Now, here we discuss the operator D, that is the differential operator. D means the differential operator. dy denote the differential operator, the differential coefficient of y with respect to x, where capital D is equal to d by dx. dy is equal to dy by dx, that is the derivative of y with respect to x. The second derivative of y is d square y is equal to d square y divided by dx, and in general d raised to n y is equal to d raised to n y by dx raised to n. Here d square y by dx square, in general d raised to n y by dx raised to n. Now, there are some relations connecting the forward difference operator delta, the shift operator E, and the differential operator capital D. We have the forward difference operator delta is equal to f of x plus h minus f of x. The shift operator E is equal to delta means delta of f of x. E of f of x is equal to f of x plus h, and dy of f of x is equal to d by dx of f of x. Df of x, not dy, df of x is equal to d by dx of f of x, that is the first derivative of f of x, which is denoted as f dash of x. The second derivative of f of x is d square f of x, that is equal to d square by dx square of f of x, that is f double dash x. In general, we can write d raised to n f of x as f n x, that is the nth derivative of x with respect to x. From the definition of shift operator, we have E f of x is equal to f of x plus h. Using Taylor's theorem, we can write this as f of x plus h by 1 factorial into f dash at x plus h square by 2 factorial into f double dash at x plus etc. That is equal to f of x plus h by 1 factorial into f dash x is df of x plus h square by 2 factorial into f double dash x is d square f of x plus h etc. This is equal to 1 plus h by 1 factorial into d plus h square by 2 factorial into d square plus etc. of f of x. F of x can be taken outside. This is equal to 1 plus h d, 1 factorial is 1, that is 1 plus h d by 1 factorial plus h square d square divided by 2 factorial plus etc. of f of x, that is equal to 1 plus h d by 1 factorial plus h square d square can be written as h d whole square divided by 2 factorial plus etc. of f of x. This is equal to, this is the expansion of e raised to h d, e raised to h d of f of x. That is e f of x is equal to e raised to h d into f of x. Therefore, we can write the identity e is equal to e raised to h d. E is equal to e raised to h d, an identity connecting the operator d and the shift operator e. Also, we have e is equal to 1 plus delta. We proved this identity in the previous sessions. The shift operator e is equal to 1 plus the forward difference operator delta. Consider e is equal to e raised to h d, and applying the logarithm on both sides, we get h d is equal to log e, that is equal to log e is 1 plus delta. By the expansion of log 1 plus delta, we have this is equal to delta minus delta square by 2 plus delta cube by 3 minus delta raised to 4 by 4 plus etc. That is h d is equal to delta minus delta square by 2 plus delta cube by 3 minus delta raised to 4 by 4 plus etc., which implies d is equal to 1 by h into delta minus delta square by 2 plus delta cube by 3 minus delta raised to 4 by 4 plus etc. A relation connecting the forward difference operator delta and the operator, the differential operator capital D. Now, we defined the backward differences. Backward differences. Consider a function y equal to f of x, and the value of this function y naught, y 1, y 2, etc., y n are given at n equally spaced points x naught, x 1, x 2, etc., x n. Then we can write the differences y 1 minus y naught, y 2 minus y 1, y 3 minus y 2, etc., y n minus y n minus 1. In general, y n minus y n minus 1. These are called the backward differences if they are denoted by del y 1, del y 2, del y 3, etc., in general del y n. Here the operator del is known as the backward difference operator. The difference table, the backward difference table is given by the values of x are, let the values of x are x0, x1, x2, x3 and x4. The corresponding y values are y0, y1, y2, y3 and y4. The first backward differences are del y, that is y1 minus y0, that is del y1, del y2, del y3, del y4. The second backward differences are del square y, that is this is del square y1, sorry, del square y2. This is del square y3 and del square y4. The third differences are del cube y3, del cube y4, and the fourth backward difference is del raised to 4 y4. Here 3, 4, 5, 5 values of x and y are given. Therefore, there are maximum up to fourth backward differences can be written. Now, we can use the notation as, suppose the value of y are given at equally spaced points a plus h, a plus 2h, etc. Then we can define the first backward difference del f of a as f of a minus f of a minus h. Here del is the backward difference operator, h is the interval of differencing. In general, we can write this as del f of x is equal to f of x minus f of x minus h. We can observe that del f of x plus h is equal to f of x plus h minus f of x. That is equal to this is our delta f of x. F of x plus h minus f of x is delta f of x. That is del f of x plus h is same as delta f of x. Now, del f of x plus 2h, which is equal to f of x plus 2h minus f of x plus h, f of x plus 2h minus f of x plus h. This is our delta f of x plus h. That is del f of x plus 2h is same as delta of f of x plus h. In general, we can write del f of x plus nh. By definition, we have f of x plus nh minus f of x plus n minus 1h. This is equal to delta f of x plus n minus 1h. that is del f of x plus nh is same as delta of f of x plus n minus 1 h. Similarly, we can write del square f of x plus 2 h is equal to delta square f of x. In general, del raised to n f of x plus n h is equal to delta raised to n f of x. Now, we have to prove some relation connecting the shift operator E and del. By definition, we have E is equal to f of x plus h, del is equal to E means E of f of x, that is equal to f of x plus h, del f of x is equal to f of x minus f of x minus h. That is del f of x can be written as, this is the definition, f of x minus, here f of x minus h, we have the identity E inverse of f of x is equal to, we have the relation E inverse f of x is equal to f of x minus h. Therefore, this del f of x is equal to f of x minus E inverse f of x. That is, del is equal to 1 minus E inverse of f of x. Del f of x is equal to 1 minus E inverse of f of x. That is the identity, we can write the identity as del is equal to 1 minus E inverse. That is, del is equal to 1 minus 1 by E. E inverse is 1 by E. That is, del is equal to E minus 1 divided by E. This is the identity connecting the backward difference operator del and the shift operator E. That is, del is equal to E minus 1 by E, or we can write del is equal to 1 minus E inverse. Now, we define another operator known as the central difference operator to represent the successive differences of a function in a more convenient way. The central difference operator denoted by small delta, which is defined by y1 minus y0, the difference y1 minus y0 is equal to del y1 by 2. y2 minus y1 is equal to del y 3 by 2, in suffix here 1 by 2, this is 3 by 2, etc. In general, yn minus yn minus 1 is equal to delta y n minus 1 by 2. The higher difference, the higher central differences are del y 3 by 2 minus del y 1 by 2, which is equal to del square y1, delta y2 minus delta y1 as delta square y3. In general, delta raised to n minus 1 y r plus 1 by 2 minus delta raised to n plus 1 y r minus 1 by 2, here r plus 1 by 2, this is r minus 1 by 2, is equal to delta raised to n y r. which is equal to, this can be written as e raised to 1 by 2 minus e raised to minus 1 by 2 of raised to n yr. We can use this alternative notation delta f of x is equal to f of x plus 1 by 2 h. By definition of shift operator, e raised to 1 by 2 is f of x plus 1 by 2 h minus e raised to minus 1 by 2 is f of x minus 1 by 2 h. This is the alternate definition of central differences. Here h is the interval of differencing. The central difference table is given by, consider the values x naught, x1, the values of x are x naught, x1, x2, x3, x4, x5 and x6. The corresponding y values are y naught, y1, y2, y3, y4, y5 and y6. The first central difference is delta y 1 by 2, here delta y 3 by 2, delta y 5 by 2, delta y 7 by 2, delta y 9 by 2, delta y 11 by 2. That is, the suffixes are averages of these two suffixes. Here 1 plus 0, the average is 1 plus 0 by 2. Here 2 and 1, the average is 2 plus 1, that is 2 plus 1 by 2, that is 3 by 2 and so on. The second differences are del square y, in suffix take the averages of 3 by 2 and 1 by 2, that is 3 by 2 plus 1 by 2 all divided by 2, that is 2 by 2 is 1. Here del square 5 plus 3 is 8, 8 by 2 is 4, 4 by 2 is 2, del square y 2, del square y 3. Del square y 4 and del square y 5, taking the averages. The third differences are, here del cube 2 plus 1 is 3, 3 by 2, del cube 5 by 2, del cube 7 by 2, del cube of y 3 by 2, here del cube of y 5 by 2, del cube of y 7 by 2, del cube of y 9 by 2 and so on. And the fourth differences are del raised to 4, here 5 plus 3 is 8, 8 by 2 is 4, 4 by 2 is 2, del square y 2, sorry, del raised to 4 y 2, here del raised to 4 y 3 and del raised to 4 y 4. The fifth differences are del raised to 5, 5 by 2, here del raised to 5, 7 by 2, and the sixth difference is del raised to 6, 12 by 2 is 6, 6 by 2 is 3, del raised to 6 by 3. This is the difference table. Now, we define another operator, mean operator. The mean operator is denoted by mu and is defined as mu f of x is equal to 1 by 2 into f of x plus 1 by 2 h plus f of x minus 1 by 2 h. That is the averages of f of x plus 1 by 2 h and f of x minus 1 by 2 h, which is the mean operator. Now, we shall discuss some relation between the operators. We have the central difference operator del f of x is equal to f of x plus 1 by 2 h minus f of x minus 1 by 2 h. That is equal to, this is e raised to 1 by 2 f of x minus this is e raised to minus 1 by 2 f of x. By the definition of shift operator, we have e of f of x is equal to f of x plus h. In general, e of e raised to n f of x is equal to f of x plus n h. We use this definition, that is equal to e raised to 1 by 2 minus e raised to minus 1 by 2 of f of x. That is, we have the identity del is equal to e raised to 1 by 2 minus e raised to minus 1 by 2. An identity connecting the shift operator e and central difference operator delta. Further, we have del f of x is equal to e raised to minus 1 by 2 into e minus 1 of f of x. From here, we take e raised to minus 1 by 2 in common. Therefore, we have del f of x is equal to e raised to minus 1 by 2 into here 1. This become e. That is e raised to minus 1 by 2. This is delta. We proved the identity e minus 1 is equal to delta. That is e raised to minus 1 delta of f of x. Hence, we obtain the identity del is equal to e raised to minus 1 by 2 delta. Or if we multiply, if we operate both sides by e raised to 1 by 2, we can write this as e raised to 1 by 2 del is equal to delta. Now, by definition of the mean operator, we have mu f of x is equal to 1 by 2 into f of x plus 1 by 2 h plus f of x minus 1 by 2 h. This is the mean operator. This is equal to 1 by 2 into, by definition of the shift operator, we can write this as e raised to 1 by 2 plus this is e raised to minus 1 by 2 of f of x. That is, the identity is mu is equal to 1 by 2 into e raised to 1 by 2 plus e raised to minus 1 by 2. An identity connecting the mean operator and the shift operator. Now, we have e del f of x is equal to e of f of x minus f of x minus h. By definition of del f of x, we write del f of x equal to f of x minus f of x minus h. By the definition of shift operator, E f of x is f of x plus h minus E f of x minus h is f of x. This is equal to delta f of x. That is, the identity is E del is equal to delta, and del E f of x, that is equal to del, by definition E f of x is f of x plus h, that is equal to f of x plus h minus f of x. By definition of del, this is f of x plus h minus f of x, which is equal to delta f of x. By definition of the forward difference operator delta, this is delta. That is, we have the identity del E is equal to delta. Here we proved E delta is equal to delta. Here, E del is equal to delta, and here del E is also is equal to delta. Therefore, we can conclude that E delta is equal to E del is equal to del E. Thank you for watching this session. We will meet again with another topic in the next session. Thank you.